Cool. I guess I'll start. Thanks for coming to the talk, everybody. I know it's the last one, so thanks for showing up. I'm Tobi, co-founder and CTO of Mesosphere, and I'm talking about Marathon and init daemon for your whole data center. This may sound a little weird. I'm going to explain what it means, promise. I'm going to start with just a little bit of background on Mesosphere. We started in April 2013. It was founded by Flo Liebert and myself. Before doing Mesosphere, we were both engineering leads at Twitter and Airbnb. And we built the services stack there as well as the data stack. And we introduced Apache Mesos to both companies. And we're also contributors to the Apache Mesos open source ecosystem. So Marathon, which is part of the ecosystem, and Kronos, another tool. Flo and I were the original authors of that. So just a quick outline of what I'm going to talk about. An init daemon for the data center, why do we need this? So I want to start with state of the art. How do we run data centers today? How do we deploy applications today? Then explain why we need a data center operating system. And then I want to go into more detail into Mesos, which is basically the kernel for a data center operating system. And then finally talk about Marathon, which is the init daemon. So state of the art, if you run a data center today, you start with physical machines, and then if you run your own data center, you might install VMware or OpenStack on it to turn your physical machines into virtual machines and then install your application on those. If you run in the cloud on AWS or Google Compute, then those providers do that for you. But one way or another, you usually get virtual machines. And the next thing you do is, you want to install your applications. So you go in and you select a few of those VMs and you say, for example, I'm going to install Hadoop on this. We typically use tools like Chef or Puppet or Ansible. And the key here is it's a manual process, right? I need to decide, I'm going to take these 9 machines and install Hadoop on it, and I'm going to configure these machines for Hadoop, and I'm not going to run anything else on those machines, right? And similarly, I'm going to set another few machines aside for example, for my web server. And then let's say, my company's growing really fast, so I'm getting a lot of traffic. I need to, make my Hadoop cluster bigger so I can process all the data that I'm producing. Again, I need to go in and edit my chef recipes or whatever, decide I'm going to use these additional machines for Hadoop and scale it up manually. Now, this process is called static partitioning, right? I'm taking the resources, the VMs that I have available, and I'm statically allocating them to the applications that I want to run. And every time I want to change something, I need to go in and edit a config file or change something else manually. Now, what if your laptop worked like this? Every time you wanted to start an application, you would see this window that asks you, on which CPU do you want to run this application? CPU 1, CPU 2, CPU 3, CPU 4? That would be really silly, right? And so, of course, that's not how it works, because we have an operating system that takes care of allocating the CPU cores to the applications that you want to run in your, on your laptop. And we want to do something similar for the data center. Now, to spell out the problems with VM-based data centers as we run them today, they're fairly complex. We get something that's called VM sprawl, which is if you start with 100 machines and you put VMs on them, you end up with 400 or 500 things that also look like machines and that you need to manage. So it increases the complexity quite a bit. And as we said earlier, you need to manually install your applications, resize your applications, scale them up and scale them down. Virtual machines as an abstraction are also very limited. They're kind of black boxes, right? You can't really figure out what's going on inside because they run a whole operating system, and that operating system may be doing whatever. We can't tell. And that makes it really hard to do smarter things like software failure handling, like looking inside of the VM and seeing, is this Java application that I'm running in there still working? That's really hard to do. Another thing is, VMs are very inefficient. Because of the static partitioning that we're doing, we basically always provision for peak load, which may happen at different times of the day for different applications. For your web app, you typically see a peak somewhere during lunchtime, and you're probably counting your revenue and running all your Hadoop jobs sometime at night. But you're always provisioning for that peak, and you have these siloed machines and never get to close to 100% utilization. Another thing that makes VMs inefficient is just the VM overhead. You need to run the hypervisor on there. That costs something. I think in terms of CPU overhead, it's somewhere between 10 and 15% today. More importantly, for real-time applications that are very latency sensitive, it's even worse. There's some numbers on the internet. It can be a factor of 2 to 3x. And in addition to the hypervisor, of course, for every VM, you're running a whole operating system. So you need to ship that whole operating system to the box. You need to start the kernel that takes memory, and so on. And lastly, and I think that's a very important point, VMs are not a very developer-friendly abstraction. It's when we build a distributed system that we have to start at the machine level. We have to take multiple VMs and kind of tie them together. And that's not great. It would be nicer if we had some more high-level abstraction. And because of all the reasons mentioned earlier, you have this manual process. It takes a really long time to roll out new software. So since VMs came around or became popular for how we use them today, our applications have actually changed quite a bit. Back in the client-server era, it kind of looked like we had pretty big servers. The first multi-core servers started coming out. And a lot of our applications couldn't really make use of those big machines, because they either were single-threaded or just not programmed for these new machines, or just didn't need that many resources. So virtualization made a lot of sense. We took this big server, split it up into pieces, ran multiple applications on it. That way we drove up the utilization. That's great. But nowadays, our modern applications like, think about Hadoop and Spark, and distributed databases like Cassandra or MongoDB, they span many, many machines, hundreds and thousands of machines. So there isn't really a place for virtualization anymore. A better abstraction would be to take all the servers and aggregate them so that the application can see them as one. And what that gives you is basically, instead of taking all those 100 machines that we have and splitting them up into more pieces, you turn them into one, and you get something that looks like a data center computer, a computer the size of your data center. And that is the reason why we need a data center operating system. If we take all our machines and we want to expose it as one, we need some software layer that does that for us. We don't want to do that ourselves, right? So when we talk about operating system, I just want to clarify some terminology and sort of make clear what I mean by data center, by operating system in this context. So what we're interested in is, every operating system has a kernel, so that can be the Linux kernel or the BSD kernel. And every Unix system has an init system. So init was the original one. There's Upstart now, which is popular for Ubuntu, or systemd, kind of a newer one. And what these things do, in case you're not familiar, this is the first process that gets started by the kernel after the operating system boots. And every other application that runs in the operating system is a child of that initial process. So, your typical Unix applications, if you're running a server, you might be running Apache web server or MySQL, Memcache, SSH daemon, whatever. Those are your typical applications there. Now, the analogy for this data center operating system that I want to talk about is we basically have the same layers. We have a kernel, an init system, and then applications. And Mesos is our kernel. I'm going to talk about what Mesos does exactly in a little bit. That's our operating system kernel. And Marathon is the init system. So, all the applications that run on our data center operating system are basically childs of Marathon. And we can run things like Rails and Redis, Elasticsearch, Memcache. Those are just examples. So a little bit of history. how Mesos came together and this whole idea of a data center operating system, how that came about. So it started in 2007 when control groups were contributed to the Linux kernel. That was done by Google initially. And control groups are a way of doing lightweight isolation. So VMs are actually really cool things because they allow us to run these multiple applications on the same machine without them seeing each other. That's actually a really neat thing. And the problem is just that it's very heavyweight. So Google came up with this idea for control groups, which give you a lot of the same things. You can isolate the amount of CPU that every application can use so they can't interfere with each other. You can isolate the amount of memory, network I/O bandwidth, disk I/O bandwidth, all those things. The difference is that it's an API in the kernel, so all the applications will run under the same kernel. You don't have this overhead of the hypervisor, and you don't have the overhead of running multiple operating systems. And this is what Google uses in the data centers to this day. It's actually also in Android. And in 2009, there was a book published called The Data Center as a Computer. That was by two engineers at Google, Luis Barroso and Urs Hölzle. Really good book. It's kind of the Bible for how to think about this. And they talk about how they do isolation, what their data center operating system looks like. A couple more things also, how they built their data centers and their hardware and so on. So this is really where the idea was born. It came out of Google, and Google has been doing this for many years. Mesos started shortly after, also in 2009, and it came out of AmpLab at UC Berkeley, actually the same lab and the same people that built Spark. And many people don't know this, but Spark was the first application that was developed on top of Mesos. And you can now run it in standalone mode, but it took them the same amount of time to build the standalone mode that it took to build the rest of Spark on Mesos. So it was designed as a distributed operating system kernel. The goal was, to have a scheduler and be able to run any, large-scale applications in a big compute cluster. In 2010, we had our first large-scale production deployment. Twitter started using it. They had scaling challenges at the time and took to Mesos as their answer. In 2012, we wrote Kronos at Airbnb. It was basically a better replacement for cron. Fixed a lot of the common problems. And the reason why we built it on Mesos was because of the goals we had for Kronos. It had to be a distributed system. It had to be resilient to failure. And Mesos was basically the distributed systems Lego that we could use to build the system in just a short amount of time. The first version of it was just under 3,000 lines of code. And then Marathon was developed at Mesosphere when we started last year. That's the distributed init daemon. And early this year, those things are pretty young, but they're happening. People started porting popular open source projects like Cassandra and Elasticsearch and Kafka to Mesos. Now, when we say distributed operating system kernel, what does that thing actually do? So here's some of the most important things that Mesos does for you. So Mesos is a cluster level resource scheduler. So what that means is it's aware of all the resources available in your cluster, how many machines you have, how big they are, how much CPU, memory, and disk, or any other resources. And it will schedule applications that want to use these resources. So it'll give the resources to different applications, make sure everything runs. It uses the cgroups API that I just talked about to do isolation between these different applications, so you can run many of them on the same machines without them interfering. It provides abstractions for launching tasks, very common thing in distributed systems that everybody sort of implements themselves from scratch every time. But with Mesos, we have an abstraction to do that, and they kind of look like threads. So we can launch them, Mesos will monitor them and tell us what happened. Did that task exit normally, or did it crash, or did we lose the machine and all that. It also gives us a way to communicate between tasks. So very common thing in distributed systems, I just need to send messages across the cluster. That's built in, it's kind of like IPC. It does failure detection, so if we lose machines or processes crash, we get notified. It has authentication and authorization, so this is a multi-tenant system, so that's really important. And yeah, like I said, it's basically Legos for building distributed systems. So it has high-level APIs that allow you to build what we call frameworks. Those are applications running on Mesos. A couple of facts. So when this thing came out of the AMP lab, they did scale testing with actually 50,000 simulated nodes, and it worked just fine. It didn't fall over. And we have the largest production deployments out there are many thousands of nodes. Mesos was designed to be highly available from the start. So there's no single point of failure in there. You can kill any single part of the system and it'll keep running. In fact, Ben Hindman, the original author of Mesos, one of his favorite things to do when he gave presentations about Mesos was to kill the production master at Twitter. So the thing that runs Twitter, basically. He killed it live in the session, and nothing bad happened. It's a top-level Apache project since last summer. Those APIs I was talking about, we have them in C++, in Python, for JVM languages, in Go, and in Haskell. There's a couple more that people are working on. We have pluggable CPU memory and I/O isolation. So that's really exciting stuff. You may have heard about Docker integration coming into Mesos. So that's how we do this with this pluggable API. And Mesosphere provides commercial support and packages for Mesos. Now, I want to talk a little bit about how Mesos does this, how it schedules applications, how it responds to failures and all that. So let's say we have a typical cluster here. We have two applications running. The two boxes on the left are just the legend. So we have a web server running and Hadoop running. And in this picture, it looks pretty normal, right? We have one Hadoop and one web server per box, nothing special there. But what Mesos can do is it can run multiple applications on the same machines if there's resources available. So an application might only need half of the box. And in our typical model where we use Chef and Puppet and VMs, we would at least have to build very complicated tools to make that kind of thing happen. And what we saw here is that Hadoop took most of the resources, and we can also make the inverse happen. So let's say we get TechCrunched or slashdotted, right? A lot of traffic on our website. What we can do is take away the resources from Hadoop and give them to the web server instead. So our website is responsive and people can see it, and we can do that dynamically and within a few seconds. Similarly, Hadoop can take over the cluster if it needs to at night where we don't have traffic on our website, but we want to crunch a lot of numbers. That can happen. So here I just put a third application into the mix. It's a Cumulo in this case, distributed key value store. Just to illustrate how Mesos deals with failure. So let's say we lose one machine here. Someone tripped over the power cord. Or, in fact, we lose a whole rack of machines because, the switch broke or whatever. So, you saw a purple box and a green box running on these things. Now, what Mesos will do when this happens is it'll automatically reschedule those applications on the extra machines that are available. No human has to do anything there. This is all automated. Now, another thing you can do with this is if you, let's say, you have very spiky workloads and you're running in your own data center, but you kind of want to use the cloud for your peak capacity, you can just add nodes to the Mesos cluster, and they can run anywhere. They can run on EC2, even if the rest of your cluster is in your private data center. And the way this works is you really just boot the machines, you start the Mesos process on it, you tell it where the master lives, it'll connect, and then Mesos will start scheduling workloads on it immediately. Cool, so this was kind of a quick overview of what Mesos does, how it responds to failures. Now to the interesting part, which is Marathon. So what is Marathon? Well, in the title of the talk, I called it an init daemon for the data center. So if we go over that, what does that mean? Well, it's like an init daemon because it can run any Linux binary without modification, which is also what init in UNIX does. Those apps don't need to know anything about the init system, and similarly, anything you run on Marathon, it doesn't need to know anything about Marathon. It's a cluster-wide process supervisor. So the same way the init system supervises processes on one machine and restarts them when they crash, Marathon does that just on a cluster level for hundreds of thousands of machines. You can also call Marathon a private platform as a service. And some of the features that Marathon has that are typical for PaaSes are it provides service discovery. So how can one application find another? It provides automated software and failure handling, so we can lose machines, we can survive software crashes, it'll respond to that automatically. And it has features for deploying applications and scaling them. So some of the design goals we had for Marathon were this. I talked about earlier, like, what are the problems with VM-based data centers? They're very complex and limited, not developer-friendly. How can we solve those problems? And so our goals were, let's really simplify this. We don't want to maintain like all these different configurations, all these different recipes for all the different apps. If we have fewer things to manage, there's fewer sources of error. It's that simple. So when you run a cluster with Marathon, you can configure all of your machines the exact same way. And not only does that reduce the complexity of your configuration system, it also means that every single machine in the cluster can be replaced at any given time, because those workloads can just be rescheduled somewhere else. Another goal was to really automate as many things as possible, because, yeah, nobody likes to get paged at night. And there's a lot of things we can automate. We can automatically respond to hardware and software failures, reschedule these applications so we don't have downtime and we don't need to wake up in the middle of the night and fix those problems. We also wanted to improve efficiency. So in a typical data center, unless you're doing something very special that takes a lot of time, you don't usually get CPU utilization across like 15% or so is kind of the typical number. So that's really wasteful. And the reason for this is that humans aren't very good at estimating the resource requirements of applications. Or we're too lazy, like we just want to write beautiful code instead, instead of saving our company money. So we can automate this, right? We can use what we call elastic sharing, and that means we basically bin pack applications onto the servers wherever resources are available. And another design goal was we really wanted to have a self-serve API for Marathon. Developers want to have control over their apps. They want to launch them themselves. They don't want to go through ops or order servers and wait 3 months. So we give them direct access to cluster resources within constraints that could be set. But basically, the developer has control over launching their apps. So the key features in Marathon are, to make this easily accessible and simple, it has a JSON REST API. Very easy to use. You can write scripts against it. It's very simple. It also has a really nice and beautiful web user interface where you can just see what's running. You can start new applications, scale them up, scale them down, and so on. It has authentication and SSL support. It's highly available, just like Mesos. So you can run Marathon in an HA configuration, lose any single node, actually lose n-1 nodes, and it'll still keep running. Even if you kill Marathon entirely, all your applications will keep running, and you could sort of just reconnect it. It'll reconcile its state. It has placement constraints. So, in theory, it shouldn't matter where your applications run, but for some applications it does. And actually, if you're running, a user-facing application, you want redundancy. You can so with Marathon, you can set constraints and say, for example, this application only run it once per node, or this other application, I want all the processes to run in the same rack because I need low latency interconnect between the different processes. So you can set all these things with Marathon's placement constraints. It has service discovery and load balancing. We ship it with a configuration for HAProxy. I'm going to go into a little bit more detail how that works exactly. And the last bit is it has an event system, so you can integrate it with any third-party components. For example, hardware load balancers. So anytime applications come and go, nodes come and go, Marathon will publish an event to an HTTP endpoint, and you can consume that and do whatever you want with that application. So just to explain sort of the common workflow with Marathon. So like I said, it has a REST API. So you define your application as some JSON, you post that to Marathon. And then Marathon, being a Mesos framework, an application that runs on Mesos, it'll go to Mesos, and Mesos will then schedule your application and run it. So, in this case, I just told Marathon, run 2 Rails processes. Marathon talks to Mesos and says, where are resources available in the cluster? And Mesos says, 1.foo.com and 3.foo.com have some, capacity that fits your application. So it's going to schedule it on those nodes. And then when you start another application, that might run somewhere else. So the play app that I started here runs on 2, and the other play process runs on 1. And again, you have some control over this. You can set constraints if you do want to influence where applications get placed. So with Marathon, there's basically 2 ways to start an application. The first way, I called it self-contained apps. So that means, if you can put your application into one single file, like a jar, if it's a JVM-based application, or just any other framework that you can, for example, put in a self-contained tarball that has all your dependencies, you can start the application like this. And you basically only need 3 things to start the application. You need to tell Marathon what the command is, so just a shell command to bring up your application. You can, the second one is optional. You can give it one or many URLs for it, Marathon, to download your tarball with the application, or download configuration files or credentials. So you can just give it a list of URLs. Every time Marathon starts an application, it'll run in a temporary working directory, and all those files that you specified will be in that directory before the application starts. And then the third one, also optional, you can set environment variables. So if you want to start, for example, a play app here, this is what it would look like. There's a play apps you can put in a zip file. So I just gave a URL to the zip file that has my application, and the command to start it is, there's a bin script in every play application. What's interesting here is I'm setting a port with this $port variable. So this is kind of an interesting bit, sort of relates to how Marathon does service discovery. What I mentioned earlier is Mesos is a resource scheduler, and we treat ports as resources also, right? You have a limited number of ports in every machine, and you can't, 2 applications can't use the same one. So we treat it as a resource and hand it out to applications, and then don't give it to anybody else. And Marathon makes these ports available in environment variables, so you can tell your app which port to use that way. And yeah, I'm just setting some secret password in the environment here. So this works well for JVM-based applications. Some people also use it to run Rails, for example. Rails is a little more complicated, has external dependencies. But with Bundler, we can also kind of stuff it all in one directory and then just make a tarball and run it this way. But the other option is you can also launch Dockers with Marathon. And Docker is, as you might know, a very popular tool for packaging an application and its dependencies into a container image. And so you basically have everything in one file again. And so to run the Docker, we only need 2 things basically. We need the Docker image URL in this format, and we can set Docker options. So here I'm like mounting a directory into the container, and I'm setting an environment variable in the container. And that's all you need. Marathon will then go fetch the Dockers, we'll start them on the machines. It will forward ports for you also, and yeah, just start the Dockers for you. Now, another common option is just scaling applications up and down. So I'm getting more traffic. I just need need more resources. And really, the only thing you have to do is just tell Marathon how many you want. You can do a patch request to whatever application you're trying to scale, and just change the number of instances. And it'll happen as soon as resources are available, which is usually immediately. So these are sort of the most interesting REST endpoints. There's a lot more, too many to cover in a talk. So Marathon also has this nice web UI. You can kind of see all the applications that are running, the commands that were started to run them, how much memory they're consuming, CPU, and number of instances. There's a button, it's a little hard to see, top right, to start a new application. And For every application, I can see all the details. So it tells me how many resources are being used by this application. I can see all the different instances of this application running in the cluster. So in this case, there's just one running on localhost port 31358. It started. Applications have different states. It'll tell you if it's staging that application right now and when it started. You have a couple actions here. You can destroy the application, which will, it's red, it'll really destroy it. You can suspend an application, which basically just scales it down to 0. And then you have a scale button where you can just put in a number to scale it up or down. And the other thing you can do, you can also look at the configuration of each application. So which command was used to start it, any constraints that are set, ports, URIs, and so on. So next I want to talk about how Marathon does service discovery. Service discovery is a very important part in for a service-oriented architecture, and there's many different ways to do it, and they all sort of have different trade-offs. And so I want to first talk about what our design goals were for what we wanted service discovery to look like. The first one was, this is the most important goal. We wanted service discovery to be as simple as possible. Really as simple as just connecting to a host and port with TCP. This is what everybody is used to. This is what every application can do. Ideally, we want it to be as simple as that. And discovery should happen transparently. So a lot of service discovery systems, they require you to use a special client. That's really horrible. I mean, first of all, you have to change your application to add that client. If you're lucky enough that there is one for the language that you're using. You have to maintain the clients also in all the different languages. So there's a lot of overhead. So we didn't want to do that. We also didn't want we didn't want the client to having to do any retry logic. What pretty common thing in distributed systems, you lose one of the nodes, but there's many other nodes you can talk to that do the same thing. And so typically, if you just retry with a different node, you'll get what you want. But that logic, we didn't want to force that upon the clients. We wanted the discovery system to handle that. The next one is the registration, which is basically the other end. When a service comes up, how does it tell the service discovery system that it's there and where it is? We wanted to do that out of band, meaning the same way we didn't want to require a client for discovery, we didn't want to have to modify the services to be able to register with the service discovery system. And because Marathon allocates hosts and ports via Mesos, we already have all the information that we need, so we can do that out of band. And the last one, very important, we wanted to do a real-time failover. So if you lose a node in the cluster and the connection fails, we're going to automatically try again, and the client won't even notice. So how does this work? Here are all the different pieces. So I have 4 boxes in this cluster, sort of the dotted lines. And I have, the top 2, I have Rails running, and the bottom I have a SQL server, a search server, and on the other box I have a search server and a cache. So the way this is exposed is we run HAProxy on every node in the cluster on localhost. And via Marathon, we allocate a known port for an application. So when you say, for example, you start MySQL via Marathon, MySQL's default port is 3306. You can just tell Marathon that to configure HAProxy to use 3306 for MySQL always. So that means MySQL is always available on localhost 3306 on every node in the cluster. So it's a well-known port. It's kind of like in the old days you did in UNIX. There's an etc services file that has service name to port mappings. And you can just hardcode that in your application because it'll never change. HAProxy updates its configuration via the Marathon REST API. So it'll just, in certain intervals, it'll just poll Marathon for, give me all the list of all the hosts and ports of application A. And then it'll update its configuration. HAProxy can reload its configuration without killing any connections. So it's very, very transparent. And the other nice thing about HAProxy, in case you're not familiar with it, it's a very, very sophisticated TCP and HTTP proxy. You can configure a lot of things. You can set different load balancing policies. You can prefer, certain nodes and all sorts of things. So if you look at the diagram, what happens is, let's say I made SQL available in localhost 306. Rails really just talks to HAProxy on its same machine, and then HAProxy knows where the actual nodes live in the cluster, and it'll find them, open the connection to them, proxy it through. So this is kind of what we recommend for service discovery, but there's other options too. And you can basically build your own service discovery system or integrate with your own service discovery system if you have something set up already. And there's two ways. There's basically a pull and a push way. So you can pull the REST API. It's basically just a GET request to v2 tasks. This is exactly what HAProxy does. That's where it gets its configuration from. The other option is you can push. So Marathon has an event bus built in. So anything it does, any API requests it gets, any nodes coming and going, applications crashing, will fire off an event. And you can have Marathon push this to an HTTP endpoint that you specify. And then in there, you can do whatever you need to do. This can be used, for example, to configure hardware load balancers. So I also want to talk just briefly about the roadmap for Marathon. Bunch of exciting stuff coming up. One thing that's it's probably going to be merged in the next few days is configurable health checks. So right now, the only health check that we do is we make sure that your process stays up. But if your process stays up and becomes unresponsive, doesn't respond to HTTP anymore, we currently can't detect that in Marathon. HAProxy will detect it, but Marathon will just keep that process running because it thinks it's healthy. So we're adding these checks to make that better. One thing that got merged recently is app versioning, and that's sort of the basis of the other two features. So app versioning just means every time you change an application, you edit something, it gets a new version, so you can roll forward and roll back. And what that enables us to do is deployment orchestration features. So being able to do sort of a staged rollout, for example, a canary model where we deploy one instance of the application, we wait till the health check gets green, and then we roll it out more, things like that. And the last one is app groups and dependencies. So a lot of times you have a user-facing application that depends on a bunch of backend services. And what you can do with groups and dependencies is you can say, for example, my customer-facing Rails app depends on MySQL and Memcache and Redis, so bring those up first and then start the user-facing application, otherwise it won't work. So we have a couple minutes left. I just wanted to quickly talk about how Twitter and Airbnb use this. So in Twitter's case, they run Mesos on thousands of machines. It's the largest known production deployment of Mesos. What it let them do is they reduced the time to deploy for new applications from literally months to minutes by giving developers direct access to the cluster. All the new production development that they do is done on Mesos. So if you're reading or writing tweets, they all go through a system that runs on Mesos. Basically what it did is it turned Twitter's own data center into a private cloud. And they were able to drive up the efficiency by a lot too. It freed up about 30% of the servers while the company was growing by 2x. And they increased CPU utilization by a factor of 2 to 3. There's a quote by Chris Fry, their SVP of engineering. He said, applying Mesos as a layer of indirection gives us a way to pack services onto machines to get higher utilization, and we can get reliability and efficiency at the same time on top of faster developer productivity as well. Another interesting case is Airbnb. Airbnb runs all their data infrastructure on Mesos, more than 4,000 cores. So they run Hadoop and Storm and Kafka, Cassandra, Marathon, Kronos, a lot of different applications that run on Mesos. It's kind of a typical modern, data analytics stack where you use a bunch of different tools versus just Hadoop. And what it let them do, same way as Twitter, they can quickly roll out new applications with this. Actually, Airbnb was one of the first adopters of Presto, a new data analytics tool that came out of Facebook. And they very easily were able to run that on Mesos and Marathon. And basically what it means for them is, they automate more things, which means they need fewer people to manage all their servers. And that's sort of their general design, engineering philosophy. So Mike Curtis, the VP of engineering, said it helps them advance Airbnb's general engineering strategy of building small teams that can move fast. And the idea is to make it so a small number of engineers can have higher impact through automation on Mesos. So yeah, those are two very visible companies that use Mesos. There's many more. If you go to the Apache side, you'll see a long list of companies. Here's some, if you're curious about this, if you want to get started, here's some links. You can try this out on AWS. You just have to pay AWS. You don't have to pay us. We have packages for all the different Linux distributions. There's tutorials, add-ons, tools, and that's it. Thank you very much. Lots of questions. We'll start here.
A quick one. You didn't talk much about storage. What does it do for disk or shared storage? Okay, yeah. My question is about shared storage, if there is any, or how does it deal? I guess Mesos more than Marathon.
Yeah, great question. So storage, it really depends on how you want to use storage, and there's sort of a couple different options. So we think long-term storage will move sort of. We'll see more distributed systems that handle storage in a distributed way. So examples are Cassandra and MongoDB. They basically have their own implementation where they make sure that if they lose nodes, data doesn't get lost and so on. And those are well supported on Mesos. The other bucket of applications are sort of, MySQL, Redis, sort of the applications that expect, I'm always going to run on the same machine and I'm going to have data at my disk available there, right? You can do that with, basically we can't make that better. If MySQL expects data to be there, what we can do is that we can make sure that MySQL always runs on that machine.
But I mean, does Mesos have any knowledge of storage as a resource, or a distributed system like Ceph?
Yeah, so Mesos only has knowledge of I/O. So we don't have knowledge of, is this piece of data available here or there? That's sort of out of band. What people typically do, for example, is they run HDFS on the Mesos cluster side by side. And you can host HDFS with Mesos. But the work of determining where data lives is sort of left to the distributed file system. The reason is just, it's really hard to build a good distributed file system, and there are a couple of options out there. So, there was really no need to reinvent the wheel. You can just run them side by side. Yes?
How does it actually work under the hood? For example, if you have a MySQL that runs on a Mesos cluster, 5-6 different machines, and you install MySQL on it and run it. Under the hood, at the end of the day, you can port as a resource is fine, but how does it actually run on each single machine that forms the cluster? Do you have 5 different instances of MySQL running that kind of federate together some way that we don't know about?
Yeah. Yeah. So again, Mesos is a scheduler, right? So if we don't like sort of make MySQL better and turn it into a distributed and fault-tolerant system, that would mean we'd have to fix MySQL, right? So you get sort of the same behavior that you get without Mesos. If you lose the MySQL master, you have to do something to fail over. Now, what you could do, there's sort of the distinction between Mesos as the kernel and then the applications, the frameworks. So, if you run MySQL on Marathon, it'll just make sure that it stays up. If you turn MySQL, if you take MySQL and you add a component to it that is built against the Mesos API, you could build things like failover, like master-master failover, or master-slave, promoting a slave to a master, those kinds of things. But you would have to, go into the MySQL code and change it.
What's the relationship between the Docker integration and Demos or Demios?
Mm-hmm. Yeah, so the relationship there is, so we released a sort of a prototype Docker integration last year in September. So it was a way to schedule Dockers with Marathon. But Docker was not built into Mesos core at that point. So it was really, basically we just called the Docker command line tool instead of, calling other commands. Now, in the next Mesos release, so there was the 18 release that came out a couple of weeks ago, refactored how we do isolation. So there's now a super API for isolation. Isolation means, you can isolate CPU separately from memory and separate from I/O. And so there's sort of a super abstraction for all these called a containerizer. So that's a first-class citizen or will be in the next Mesos release 19. And so what Demos is, it is one of those containerizers that you can now plug into Mesos. So basically that makes Docker a first-class citizen on Mesos and one way to isolate resources. So that's the relation there. Does that make sense?
But it's a different dimension than like using Marathon as running a Docker application. It's like, you're using it just to contain something and then launch an application in a Docker container versus using a Docker container as a unit of application.
Right. And so the way it would work is there's basically two modes of operation. If you configure, so the way you configure Demos is basically you configure your whole cluster to use Demos as a containerizer. And what that does is when a node sees a request from Mesos that says, launch a task, it'll look at the task definition, it's called the task info, and it'll look at, did you specify a container image? If you did that, it'll use that container image. If not, it'll fall back to a default image that you can configure. So you can just say, if the user didn't specify a Docker, just use the default Ubuntu Docker, for example. Mm-hmm.
Does Marathon support, as part of deploying new application nodes, the notion of orchestration of validation before putting services into service? So if we're doing new code deploys, I've got 100 nodes I want to deploy. I start with node 1, deploy it, do smoke tests on it offline, then put it into service.
Right. So yeah, those are things that are on the very near-term roadmap. One thing that's going to ship in just a few days are health checks. So we can actually, make an HTTP request or a TCP connection to the service and make sure it's healthy, and only then roll it out more, or delete the old version of the application only when it's healthy. And in connection with that, we're also implementing, rollout strategies where you, for example, the canary model that you just described, where you put it on one node, you do the tests, and then you go on. So that's on the roadmap.
Thanks.
Yeah, I couldn't quite tell in your slides, but does Marathon handle dynamic scaling?
Auto scaling?
Yeah, is there a feedback request? Like, say I deploy 3 rails, but there's a number of requests that come in. How does it determine when it's over a certain threshold of the resources of a compute box, and then say go to 10?
Right. So it doesn't currently handle that. We sort of put that a little later in the roadmap. The goal was to have something working first and sort of give you the very basic abstractions that you need to build this kind of thing. So scaling up, scaling down, those are all abstractions that we have. So if you need that today, you could script against the Marathon API and make that happen. So you could ask Mesos for how much is this application actually consuming? Is it hitting its limit? And then go back to Marathon and say start more. But you would have to script it right now.
But it would understand to not scale out onto a compute box that has reached its resource limit, say in RAM, right?
Absolutely, yeah. So there's 2 limits. You have the whole box, and then for each task you have a limit that's enforced via control groups. So an application can only basically hit the limit of the control group. It can never break out of that and use the whole box. So as long as there's still resources available on the box outside of this control group, we can give those to applications.
And a real quick one, Mesos itself, is it a bare metal install? You talk about it as a kernel.
Yeah, good question. So we call it a kernel and we call it a data center operating system, but it still needs Linux as an operating system. So basically think about it, it's an operating system at a different level. So we still need Linux. So the way you install it is via apt-get, for example, or RPM. Questions over there? What distros will it run on? So we have today we have packages for the most popular ones. So we have recent Ubuntu versions, both 13s and the 12s. I think we don't have 14 yet. We have Rel 6. We have CentOS. We have Debian. There's a macOS package as well. Yeah, I think those are all the big ones. Yeah, have we looked at CoreOS? We did, yeah. We don't have a package for it yet, but it's a very exciting project. Question over there.
So when you, in that one example with the play where you just were distributing a zip, I mean, would that executable be able to see anything else in the file system? Or is that just isolated to whatever was in that zip? As opposed to, if you're distributing a Docker container, it has that whole virtualized, Linux distribution it can see.
Right. Very good question. So can all the other applications see the zip file or whatever I'm doing there? It depends how you configure your cluster. So we can use chroots basically to really strongly isolate different applications from each other. What's always going to happen is that you're always going to be running in a temporary working directory. So as long as you're not malicious and you're trying to break other applications, you won't see them because they have some random path as their working directory, and that's where all the files live.
And for the Docker integration, I mean, is every Docker distribution going to be its own Docker host, like just one Docker host and one Docker container? Or is Mesos, like the host OS, the Docker host, and then each container just runs in that?
Yeah, so we're running multiple Dockers on the same machine. Yeah. So
multiple Docker hosts?
What do you mean by Docker host? Docker daemon?
Yeah.
Yeah, so there's one Docker daemon per physical machine. And yeah, all the Dockers that run on that machine will be connected to that daemon.
How do you deal with the version upgrades of Mesos and Marathon?
Very good question. Version upgrades. So that's a very important feature and one that Twitter contributed because they do that all the time in production. So kind of back to the idea of building it as a system without a single point of failure. You can so Mesos runs a process on every node in your cluster, and if you want to upgrade that, you can just kill that process. All the tasks that it was running will continue to work. So all the web apps, whatever you're running, databases that Mesos started on that box will continue to run. So you can just put the new binary on the machine, bring it back up. It'll reconnect to the master, and the tasks that are running will also it'll find them again basically, and then it'll push its state upstream and say I'm back. And so within a failover timeout that you can configure, things will just keep running. With the masters, it's the same way. Like I said, we can do master failover without doing any harm. So what you would do is you would just start with a master that's not the leader right now, shut that down, replace it, shut down the other followers, and then eventually shut down the leader. With Marathon, it's similar. So you can kill the Marathon scheduler and bring up a new version of it, basically. Everything will keep running. The only thing that's not going to happen while you're bringing up the new version is that obviously the REST API will be down for a short time. But yeah, it won't kill any applications while you're upgrading.
Okay, so it's tolerant of mixed versions running at the same time to facilitate rollout. Okay.
Yep.
You described the combination of Marathon and Mesos as a private PaaS, and at the end you had mentioned that you could use this in Amazon. I was just curious, or wanted to confirm that can you use this in a hybrid model, let's say between your private data centers and Azure, for example? Absolutely.
So from a Mesos perspective, Mesos really doesn't care where it's running as long as it's a relatively recent Linux. Or actually Linux 2.6+. It also works on Solaris and macOS, but it doesn't have all the features like control groups. So whether you start that Linux on AWS or in your private data center, or on OpenStack, on VMware, Mesos doesn't care. You'll get most of the performance on bare metal though.
So, it seems like so many people that are running or building platform as a service, they're the ones hosting it. I'm kind of in a situation where we're kind of going to this microservice architecture, but we're giving this to someone else to run. And so this kind of seems like a nice container to just build around the whole thing, where you just say, like, run this Mesos operating system, and just like you would say, install this RPM and run this one process. Are people doing this kind of thing, or?
Yeah, absolutely. So we're working really hard to make it actually as easy as you just described, where you just install an RPM and it'll start running. Not quite there yet, but soon. But people do that. You know, I talked about Kronos earlier, which was a cron replacement that we built this at Airbnb and open sourced. That sort of you know, fixes a very common problem that people have. It seems like most people run their data pipelines with cron, and it breaks all the time. So people use Mesos just to run Kronos, which means, you know, they just install it on a handful of hosts, like 3 hosts, and it's fairly easy to set that up. Yes, question over here.
So just to kind of try to understand this, even if I had 100, even if I had a cluster of 100 machines running Mesos, then the maximum size of, for example, MySQL database that I could run would be limited by the size of the largest machine I have in my cluster.
That's right. So under the covers, we still treat separate machines as, you know, as separate machines. We just don't expose it that way. But we don't have any magic where we can sort of, you know, combine the memory and CPU power of different machines into one and make one application, you know, one application like MySQL run on those machines. If an application wants to use multiple machines, it needs to be programmed that way, you know, like Cassandra or Spark or Hadoop. But things like MySQL just can't do that.
So we'd be kind of, if you wanted something like that, we'd probably have to look at Amazon, one of the, was Elastic Compute, or not Elastic Compute, whatever their database, a big
RDS.
RDS.
But RDS also doesn't solve that problem because, again, it's a limitation of MySQL. So whatever you do, you can't break out of that limitation. So RDS will run it on, you know, the biggest boxes that Amazon has available, but that's it. That's the limit also. And maybe to explain that a little more, so there's basically 2 ways to integrate with Mesos. If you run on Marathon or Kronos, if you want to schedule jobs, put very simply, you usually don't have to change your application in any way. But obviously, you have this abstraction layer in between. You don't get direct access to Mesos. So if you want to use all the features in Mesos and, you know, whatever those may be, you need to program against the Mesos API. And again, so if you would fix MySQL and build it again, you know, build it against the MySQL the Mesos API, you could do these more advanced things like failover.
Are you aware of any Linux kernel level things that are actually coming up to, like you have multiple cores, like spanning multiple machines, where that will subsume the effort that you're doing in the Mesos level?
Yeah, is there, I'm not aware of anything like that. I know there is, it's very researchy things are there. I think it was Google, they came up with something where you can basically access another machine's memory at almost the same speed as accessing your own memory. But that's very researchy right now. Another question here.
Is it fair to say that Mesos and Marathon kind of sits at a layer above the virtualization management frameworks? So if it's like OpenStack or Zen or whatever, so Mesos itself doesn't spin up new VMs, but rather you allocate pools of already existing VMs to Mesos?
That's right. So Mesos, if you are using VMs, we sit on top. But the thing is, you don't really need VMs if you use Mesos, because Mesos gives you, you know, pretty much all the same benefits and more. It's, you know, we say we can run on top of VMs because, you know, you might have VMs, OpenStack, whatever, deployed in your data center, and you might not want to change that right away. So you can put it on top. But, you know, of course, you'll have the VM overhead. You'll have the hypervisor overhead and all that. You still get most of the benefits. Like Mesos will still do its bin packing, which gives you most of the performance, the efficiency win. But you will have that overhead. You know, just a number actually from a customer. They are running on AWS, so they are on virtual machines, They switched, they have very, microservices, service-oriented architecture, probably 100 services. And they moved to Mesos, and their AWS bill was cut in half. Question in the back.
More of a statement, I guess. There's nothing stopping you from having an application running in Mesos to acquire, provision new Mesos slaves and adding that to the cluster, which is how I use it myself. Just in reference to the previous, so you could have something that elastically adds slaves to Mesos in general.
Absolutely.
And that very application that's doing that can actually run in via Marathon in Mesos to do that.
Exactly. So adding capacity to the cluster is as simple as bringing up a new machine, starting the Mesos process. That's it. Question?
So at the beginning, you mentioned that a couple of users have customized existing pieces of software like Cassandra and Kafka to better adapt to Mesos. Can you describe like some of what those customizations look like in terms of how you would make things run better on Mesos?
Yeah. So it really depends. Sort of, it's sort of a case-by-case thing. It depends on what that application does, and a lot of these distributed systems like Cassandra and Elasticsearch already do things like, failover and they lose a node. So you don't necessarily want to rewrite that. The first, and those ports are really early, so they're not production ready. So the first pass was sort of just getting it up and running. So just, saying, okay, I want to start a 4-node Cassandra cluster. Give me the resources to do it. That's basically it. Now, things you could imagine in the future are, auto-scaling. So, Cassandra has metrics on, the load of the different nodes, how much data it's storing, is it running out of capacity? So if, the Cassandra framework could go to Mesos and say, look, I have crazy write throughput, I need another node. And then you would scale up to another node. Same way with, say, Elasticsearch. You need more capacity, more throughput, whatever. You could control that then. Yes.
So just to follow up, it sounds like in that case, the patch wasn't to Cassandra to run on Mesos. The patch was to Mesos to know how to deploy and scale Cassandra as a product, right?
So the patch was actually to Cassandra. So basically, what you typically do is, every one of these frameworks has like their main method somewhere. So you would go in there and basically replace the main method. Instead of like bringing up the cluster in there, the first thing you do is you connect to Mesos and you ask for resources and kind of hook in there. So it is a patch to the application, not to Mesos. Because Mesos, so that's kind of a philosophical thing, and but very important. So Google has a similar system to Mesos. It's a little older and not as advanced. It's called Borg, or Googlers will say it's the system that will not be named. Borg is a monolithic scheduler. So the Borg kernel is able to run all the applications that Google runs. So that's request response type workloads, real-time batch processing, databases, anything. And they sort of noticed that this doesn't, is pretty hard to maintain, this one piece of software that has all these different scheduling mechanics. So Mesos has a different design. It's kind of, it's a 2-level scheduler. So the Mesos kernel, all it does really is, allocate and distribute resources. And how an application uses those resources is up to the application. So that means you always have this part in the application, to talk to Mesos and make the scheduling decisions. Puts a little more burden on the application developer, but I think it's more maintainable and more flexible in the long run. All right, thank you everybody for the questions.